to generate samples from a probability distribution on a stratification. And I'll tell you more precisely what that is. But for now, very briefly, a stratification is a collection of manifolds of different dimensions. So Tony told us how one method to sample a submanifold defined by a collection, the level set of a collection of scalar functions. A stratification is a union of such submanifolds, and they could have different dimensions. In my method, the manifolds will have to be connected. So one manifold will be the boundary of another manifold. Part of what I talked about is joint work with the following people. Jonathan Goodman, Emilio Zappa, say a little bit about work with Rebbe, and it was funded by the DOE, the NSF, and the Sloan Foundation. So before I start, let me tell you a little bit about my motivation for developing this method. I'm interested in colloidal particles, which are particles that have a diameter of about a micrometer. Could be more, 10 micrometers, could be less, 100 nanometers, somewhere in that scale. So they're much bigger than atoms. We can, in particular, big enough that we can treat them using classical methods, but they're also much smaller than us. I'm going to play a movie that shows a solution, a suspension of colloidal particles in a fluid. The fluid is probably water. You see that the particles are small enough that they feel the fluctuations of the fluid, jiggle around, okay? Like Brownian, do a Brownian, they do a random walk. They can also interact with each other. So in this movie, you see the particles sticking to each other and forming clusters. This is just a raw microscope, so you can see these particles with your eye if you look at a microscope. Colloids are studied quite widely, experimentally, in science because they form the building blocks for a lot of different materials. And I'm showing some of these materials here. Question, can you see the mouse when I move my mouse?
Yeah, we can see it. Yes.
You can see it? Okay, good. One reason people are interested in studying colloids is they want to use them to make new materials. The colloids are the same scale as the wavelength, so they're interested in making optical materials. They're also the same scale as many processes in biology, so they're interested in making devices with biomedical applications, like little nano robots or drug carrying devices, things like that. So a theoretical question or a scientific question is how can we design colloids? So by design, I mean their shape, their size, or their interactions, so that when we put them in a box and shake it up and we open it, we get the structure that we want to assemble. So colloids are quite easy to study experimentally, as I mentioned, because we can see them in a microscope. Here's just a fixed idea. This is an experiment that we did where we were with a graduate student, Rebecca Perry, where we were studying transition rates between colloids. These colloids are diffusing around on a glass surface, so they're effectively disks. And they're not actually colored. We added the colors after. The rest of the movie is real. And if you watch one of these clusters, you see that it forms kind of packing of disks. But every so often, the packing gets a little bit floppy, it changes, and it becomes another packing. So how do we describe colloids? They're actually, so the energy and the dynamics of colloids are quite known. The energy is given by the stationary distribution is given by Boltzmann distribution, and the energy here, V, is the sum of pairwise interactions between colloids. That's a very good approximation. And the dynamics, a good approximation for the dynamics is the over-damped Langevin equation, which I've written here. This is not just a method to sample the stationary distribution, it actually is a good model for the dynamics of colloids. However, this pair potential view for many kinds of attractive interactions has the feature that it is very short range compared to the scale, the size of the colloids. Okay, so here I'm plotting a sketch of a pair potential from an experimental paper. The colloids in the experiment had a diameter of a micrometer, and the range over which they can feel each other and stick to each other is about 80 nanometers, probably a little less. So that's very narrow compared to the size of the colloids. So here I'm going to just play this. So the energy landscape, instead of looking like the figure on the left, it's nice and smooth, it looks much more like the figure on the right. It's very, very narrow, steep basins connected by flat stuff in between. And the energy landscape can be even worse. The local minima themselves could be energetically flat. So a good picture to have in mind is of a golf course, where the low energy states are the golf hole, very narrow, very deep, and the stuff in between is relatively flat. So because there's such a scale separation between the size, the attractive interactions, the scale of the attractive interactions and the typical length scales of interest, it's convenient to model colloids in attractive interactions as constraints. Okay, so whenever two colloids become close enough and they're interacting, you can treat that as a constraint on the distance between the colloids. And this limit can be formulated more precisely, and you can show that in the limit of very narrow but deep pairwise interactions, the stationary distribution for a collection of colloids becomes the following. This is an effect of delta functions. You get a delta function whenever a pair of particles, pair I and J, is in contact. Here, Qij is the distance between particles. If a pair is in contact, its energy comes with the factor kappa for that contact. So kappa is like the strength of the contact. And then there's an indicator function that prevents particles from overlapping. Okay.
Miranda, can I interrupt you for a moment?
Yes.
So presumably, dynamically, they don't form the bonds unless they somehow approach each other with sufficiently low velocity, right? I mean, if they just carry them into each other, they probably just carry them off, right?
So interestingly, coming back to this overdamped equation, velocity in these systems has such a short correlation timescale that it effectively doesn't matter.
Okay.
So the velocity decorrelates extremely quickly on the same timescale as velocity in the fluid decorrelates.
Okay, so they're sort of very, you would say they're very sort of dense systems, are they?
No, just that the friction with the fluid dampens their velocity so quickly.
I see. Okay.
That it doesn't matter. So that also because they're in a fluid, they can never actually hit each other. Okay. They're not like billiard balls. They can't actually approach close enough to actually touch.
All right.
If you push fluid in between two flat surfaces, the increasingly large force of bring closer together. Okay. Yeah. So there's no velocity. There's no velocity in these systems effectively. So I just want to say a few words about this stationary distribution and try and illustrate it with some pictures. So suppose we have 3 disks in R2. One way that they can be, one type of configuration is where all of the disks are not touching. Okay, so they move around anywhere in the plane or anywhere in the bounding box. They don't touch. Okay, this stationary distribution has the density on all of the different ways they can move around, subject to not overlapping. However, I could also put 2 disks in contact. Here, disks number 1 and 2. Okay, when that happens, the energy of the system is lowered by amount kappa, or kappa 1, 2, the strength of that interaction. And the stationary distribution has a singular component on the manifold of configurations where disks and 2 are exactly in. I could also put two pairs of disks in contact. So here, 1, 2, and 2, 3. Now the energy of the system is lowered even more. So it's now lowered by two factors of kappa in the stationary distribution. And the stationary distribution has a singular component on this submanifold of convention 2, where disks 1, 2, and 3 are in contact. Okay, similarly, I could put all 3 disks in contact. I get a singular contribution from that submanifold 2. And of course, I can also consider the contributions from the submanifolds where disks 2 and 3 are in contact, disks 1, 3, 2, 3, all possible combinations of ways to put disks in contact. And the stationary distribution is the sum of contributions from all of these different submanifolds. So it's a sum of many, many, many singular densities defined on different manifolds. Please stop if you have a question. So just to fix notation here, mu is going to be a Hausdorff measure on a submanifold. So mu here, mu1, 2 is the manifold on the measure on the submanifold where disks 1 and 2 are exactly in contact. Okay, I'm going to use I to represent a set of edges. Actually, I'll generalize that in a moment. Mi is the manifold where all of the pairs of disks and forces in set I are in contact. And I also included a function f here, which I'm going to go into, but we need this we need this to account for the fact that the constraints are actually a little bit sketchy, they're not perfectly hard constraints. And there's an expression for f, but I won't talk about that now. Okay, so we want to sample a probability distribution of this form, which has a component on many different manifolds of many different dimensions. So here's the mathematical setup. I'm going to explain this setup. It's fairly abstract, and then I'll give many examples to illustrate it. So we start with a list of functions, script Q, just a list of functions from Rn to n. We assume continuously differential. Then we choose subsets of Q, IEQ, which I'll call constraints, and these are going to be our equations that define the submanifolds, and then IN, which are the inequalities that define the submanifold, that are also associated with the submanifolds. And I'm going to form a pair I, which is the set of constraints and inequalities for a given manifold. Then I form a manifold M sub I, which is the set of all x's in ambient space such that the equations in IEQ are satisfied exactly. Q of x is 0 is 8, and such that all the equations in the set of inequalities are strictly greater than 0. So this is a manifold, depending on the labels I choose I. I will do the assumption that if I look at the gradients of the constraints, the set of functions in IEQ, that the matrix formed from the gradients of the constraints has full rank everywhere on M sub I. And I need that assumption, and it doesn't always hold, and it doesn't hold in interesting cases, but we need it in order to proceed. To form a stratification, what we do is we look at many different kinds of labels. We look at many different possible ways to choose constraints and inequalities. And so we have a collection of labels. And then the stratification is formed from the union of all of the manifolds defined from each of the labels. So colloquially, it's a collection of, the stratification is a collection of manifolds of different dimensions that are glued together in a nice enough way. So when one manifold is on the boundary of another manifold, it locally looks like a cone. So that's a stratification. That's a geometric object that we'll work with. On top of that stratification, we have a probability measure. And this is formed from a sum of Hausdorff measures on each of the manifolds in the stratification. So mu I is a Hausdorff measure on mi, and we might have a weight function, which I'll call si. And what I will do is show a method to generate a Markov chain on my stratification such that it has stationary distribution here. So please do stop me if there are questions. Okay, so let me show a simple example of stratification to illustrate the notation. So in this example, I'm going to start a parabola and a line. So I have two equations. One equation is y minus x squared, which if it's equality, I get this red curve. And the other equation is 2 minus y, which if it holds exactly, I get this yellow curve. And then I'm going to form stratification by thinking about all the possible ways to choose each of those functions as an equation or an inequality. Okay, this is all the possible ways. So one way is both these equations are inequalities, and that's the blue side here. Both of these equations are strictly greater than 0. That's the blue side. Another way is that the first function can be an equality, and the second one can be an inequality. And then I get the red set, which is one-dimensional manifolds. I could also think about the second one being equality, the first one being inequality, in which case I get the yellow set, also a one-dimensional manifold. Or I could think about both of them being equalities, in which case I get 2 points that are purple, and that's a zero-dimensional manifold. And I'm going to define a probability measure on this stratification, which is just a sum of Hausdorff measures on each manifold. So on the right here, I'm showing points sampled from the stratification from this measure. Okay, so you see I get some points in the interior. I get some points exactly on the line. I get some points exactly on the yellow line, and I get some points exactly on the corner. And I've kind of plotted them in a circle just so you can see the points, because otherwise they're all in the same place. Okay, and this collection of points comes from the output of my algorithm, which I'll describe in a moment. Here I'm just showing histograms on each. I'm showing the marginal distribution in X, conditional on being H manifold, just to see that I'm sampling the right thing. Okay, so right now I'll give a very brief description of how the algorithm works. I mostly want to spend time introducing other examples. Toward the end of the talk, if there's time, I'll describe it in a little more detail how it works. So roughly, the algorithm is a combination of sort of two things. One is a method that takes a step on a single manifold. So as Tony Yev described, it does a random walk on a single manifold. However, it also is allowed to jump to another manifold. And the way it does this is it detects if it's close to a boundary. If it is close to a boundary, then it might propose to jump exactly to that boundary. And it does that by adding a function, adding a constraint. If it is walking along a boundary, it can also decide to jump to a higher dimensional boundary, and it does that by subtracting a constraint. Okay, so it does three kinds of moves. One is it steps on a single manifold. Two, it adds a constraint and tries to jump to new manifolds. And three is it subtracts a constraint and moves on that higher dimensional manifold. Okay, so that's the end of my description for now, and I'll come back to this and show some equations at the end of the talk. Let me show an example of sticky spheres. So this movie that I'm playing right now is a Brownian dynamics simulation of 6 spheres interacting with stiff potential. So I think it has basically a spring potential on its backbone. And if 2 other spheres come into contact, there's a very short range of potential that will bind them together. So you see a bond has formed here. If I ran the simulation, if I run the movie for longer, you see bonds will form, bonds will break, and so on. Okay, so this is Brownian dynamics, just simulating the overdent law from the equation directly using Euler-Maruyama. I'm on the right. I'm going to show what the stratification sampler does, and so the movie will play at 24 frames per second. Each frame of the movie is 1 step of the algorithm, and each frame, the stratification sampler takes the same amount of time on a computer to sort of generate that proposal step as each frame in the Brownian dynamics simulation. So these timescales in the 2 movies are comparable. They're showing you how much time it takes a computer to generate each of these updates. Okay, so this is the stratification sampler algorithm for the same system. And now you see that bonds are breaking and forming pretty rapidly, and the cluster is deforming with given bonds. So if this is the only thing that you get from the talk, I hope this without numbers, I think you can see that this is faster than Brownian dynamics, and it's a lot faster. I'll give some numbers to show roughly how fast it is, but it's a lot faster. It is limited though, so I'll talk about, I'll describe its limitations also. Okay, so in real life, we want to simulate a squishy potential. We don't want a delta function. So this slide is to convince you that the stratification sampler is a good approximation for a squishy potential. So what I'm showing in this plot, on the x-axis, this is the strength of, this is the same system in the movie. So a backbone, a polymer, which can then form break other bonds. On the x-axis is the strength of the bonds, and I'm assuming it's all the same. And on the y-axis, the probability to find the system with a certain number of bonds. And if I don't break the bond backbone, then the minimum number of bonds we can have for spheres is 5, and the maximum number of bonds that can form is 12. And I can get any number in between. So to generate the curves come from the stratification sampler, and they were generated by running the stratification sampler once at value kappa equals 2, and then reweighting the data in a similar way to importance sampling to generate curves at all other, to generate the curves at all values of kappa. The markers show out from Brownian dynamics simulations at different values of kappa. And so this shows that you see that the markers are right bang on the curves. So this shows that we're getting the right probability distribution for a real system with a real sheet potential, even though we're treating the interaction as constraints. Okay, just a word on the efficiency. So using the same simulation and the same system, we can compare the efficiencies of Brownian dynamics versus stratification. And of course, this depends on the particular potentials that I choose. So there's a lot of details under the hood here. But for this, what I showed you in the movies, this is the comparison. So we estimated probabilities of being in each, having a certain number of bonds from the runs. We then estimated error bars on that by binning the data. And we computed the ratio of the error bars, Brownian dynamic error bar to stratification sampler error bar. But then the simulations took different amounts of time to run. So for this particular run, Brownian dynamics took 5 hours and stratification sampler took 13 0.6 minutes. And so if we want to compare the amount of physical time it would take for each method to have the same error bars, then we need to look at the ratio of actual times and multiply by the error bars squared, the ratio of the error bars squared. So this is an estimate of how much faster the stratification sampler is than Brownian dynamics, and on the same computer, in order to have this sort of the same error bar for the quantities that are being estimated. Okay, so you see it varies from a minimum of about 150 up to over 1,000. Okay, here's another example. So some scientists are interested in polymers that stick to surfaces. And if they stick only to surfaces, then they can bind and they can unbind. So we created the stratification by making a polymer with fixed bonds. So just a string of beads, as you can see here. And then also we allow each bead to bind and unbind to a surface, a flat surface. Okay, so these are the functions in Q surface. Okay, and then we formed a stratification thinking about all the ways that the polymer, that each bead of the polymer can bind and can unbind. We sampled two different distributions, two different probability distributions. One is for really jointed polymer, where the beads don't interact with each other at all. We're just looking at actually the Hausdorff measure on each manifold. And this is a picture from the this is a sample drawn from the equilibrium distribution. So you see some of the beads, the blue ones are sticking on the wall, and the green ones are off the wall. We can also study a semi-flexible polymer. So this is where there's some energy penalty for bending the polymer. So there's an energy that depends on the angles between each of the beads and the springs. And here's a sample from the equilibrium distribution of that pulp. Okay, so we can measure different things. Here we're measuring the fraction of particles on the wall as a function of sticky parameter, the stickiness of the wall. Here we're measuring the radius of gyration of the polymer, also as a function of the strength of the interaction with the wall. So we can measure different things using this. One reason I bring up this example is it's easy to study in the limit as n gets larger to see how our algorithm scales with n. And unfortunately, it does not scale very well. So here's n. Here's the time it took to generate 10 to the 7 points for different values, 10 to the 7 sampling points for each value of n. And the slope on a log scale is about 2.5. So it doesn't scale very well with n. One of the reasons for that is that you have to do a lot of linear algebra calculations in order to account for the constraints. So it's this same problem would come up even in if we're just sticking to one manifold. So I understand there are techniques that have been developed to help solve these equations more efficiently. So by solve, I mean when we're projecting back to the manifold, how do we do that efficiently? We have not implemented those at all. So the implementation that I've been using is very naive. It uses dense linear algebra. We use Newton's method. It's kind of the simplest thing you can imagine, but it does not scale well. So I'd be interested in learning about how to make this more efficient for larger n. Okay, I have a couple examples. So coming back to this question of self-assembly, so how do we design interactions between particles so they assemble into some structure that we want? If I have a polymer of spheres, so here's 6 spheres, there are 2 possible lowest energy states. One of them is the octahedron, this guy, and then one is the polytetrahedron, which is this guy. Both of these have 12 bonds. So they're both the lowest energy structures that can form if the interactions between particles are strong. However, the octahedron only occurs with 5% probability, whereas the polytetrahedron occurs with 95% probability. So much, much higher chance to see the polytetrahedron than to see the octahedron. I won't really talk about why, but very briefly, the reason is that the octahedron has higher symmetry. And so there's far fewer ways to make the octahedron by permuting particles. Or in other words, there's more different copies of the polytetrahedron that you can get by permuting particles. So one question asked was, well, if I want to make the octahedron, how can I do this? And can I do this with a simple number of building blocks? So other people have shown that if you make all particles different, then you can do anything you want, or almost anything. So we said, we asked, can you make the octahedron with only 2 types of particles? So we looked at a chain where we have A particles and B particles. B's are at the end. And we have different parameters for the AA interactions, the AB interactions, and the B interactions. And from our one sampling run with identical sticky parameter, identical strength of the interaction, we can take that data, we can reweight it, use non-identical interactions, and estimate the probability of forming the octahedron for different choices of interaction parameters. And that's the plot that I'm showing here. Here, the BB interactions are weak. This is the AA interactions. This is the AB interactions. And you can see that if the AA interactions are some order 1 value, and the AB interactions are strong, then there's very high probability of forming the octahedron. So the answer is yes, we can do this. At least for this example, we can use the stratification to help us design interactions to get a certain structure. This is my last example. One more thing you can do with this algorithm is that you can use it to estimate dimensional volumes. So to illustrate, suppose you want to know the surface area of an ellipse in a high dimension. So here's the equation for an ellipse. You can get this in other ways, but to illustrate it, we'll do it using sampling. But it's hard. There's no simple formula for the surface area of the ellipse. So here, A1, A2 are the semi-axes of the ellipse. So what we can do is we can sample the ellipse, the surface of the ellipse. We can also do a stratification by intersecting the planes. So we add planes 1 by 1 until we have enough planes intersecting the ellipse that the solution to the whole set of equations is a set of points. And we form a stratification from the ellipse plus a plane, ellipse plus plane plus another plane, and so on until we get down to points. Okay, here's an illustration in 3 dimensions. If I want to know the surface area of the gray surface, what I do is I intersect it first with the blue plane. That creates 1-dimensional manifolds. And then I intersect with the red plane, and that creates 0-dimensional manifolds, which is the set of 2 points here at the end, 1 point there and 1 point there. So now, if I sample the Hausdorff measure on this stratification, then I can use the point sampled to estimate the ratio of volumes, or the gray set to this 4-dimensional point. Okay, and the number of points in the gray set, that's this thing here on the top, divided by the number of points in the lowest dimension set, is the ratio of volumes of those sets. And since I know the volume of a set of points, it's just the number of points in that set, I can solve to get the number to get the volume of the object I'm interested in. So I did this just to illustrate for n equals 10 with semi-axes. I can estimate the volume, get some number for the volume. In order to check this was correct, what I did was I formed a different stratification, which is the gray surface and its interior, and I sampled that. And I know the volume of the interior, so I can solve to get the volume of the surface as a ratio of points in each set. Okay, so this estimates another number which is pretty close to the first one. Okay, but you can't. The green one obviously has a lower error bar. It's simpler. It's a lot faster. But usually, if you have a high-dimensional object, you don't know the volume of its interior either. So we just got lucky for this ellipse. Okay, so those are my examples. I'm going to talk very briefly about how this works. Does anyone have any questions before I go on?
Yes,
Nope.
yes, Tony has one.
Tony has one, okay.
Maybe I have one question about, so you showed that using this stratification of manifolds, you get probability measures, invariant probability measures, which are roughly the same than with Brownian dynamics.
Yes.
What about the dynamics actually? So, because I can imagine that in some situations you are also interested in building some octagons, but within a reasonable time. So,
yes.
Are you able to make this reduction to rigid constraints in such a way that you keep the dynamics correct? The typical time
Yes.
to go from one.
Yes. No, that's an interesting question, and yes, we can do it.
Okay.
What you get is you have what's called a sticky Brownian motion. And so you get a diffusion on a stratification, but the diffusion has boundary conditions. Whenever there's one manifold that is at the boundary of another, you get a diffusion equation that has what's called a sticky boundary condition at that boundary. So we've written a few papers on this, which I can send you. I think it's much easier to think about a one-dimensional sticky Brownian motion than to think about a high-dimensional sticky diffusion process. And so we have a paper that that I can send you which describes that case. But just very briefly, if I have a Brownian motion on a half line and it's sticky at the origin, essentially what that means is you can get that by taking a regular Brownian motion that reflects at the origin and slowing it down at the origin, doing a change of time. And the change of time comes from the local time of the Brownian motion at the origin. And so you change the clock when it's there. And you can do that in such a way that it slows down just enough that it actually spends a finite amount of time at the origin. So a sticky Brownian motion is like a reflecting Brownian motion that's slowed down at the origin in such a way that it actually spends a non-zero amount of time exactly at the origin. So we understand the dynamics. What we don't understand is how to simulate them. And so that's something that we've been working on with Nawaf Rabi. It's an interesting question because there's no simple way. There's no way to discretize to change Euler-Marigama so that you could jump exactly to a boundary and get the right boundary conditions. So yeah, something we've been thinking about, but we don't have the answer right now in general.
I have a question as well related to this. I mean, I guess that this last thing you said, it reminds me of this like hybrid, like Brownian simulation methods where you kind of jump from a continuous Brownian motion to some sort of lattice-based motion, and then you need to worry about the boundary conditions and kind of getting the flux right. So I don't know if that's one thing, but I had another question with the those simulation results you showed with the stratification versus Brownian motion with the bonds. I don't understand why stratification is slower. Slower with 12 bounds than with 10 bounds.
Why is this? Yeah, oh no, sorry. Are you talking? Do you mean this plot?
No, the first this one, yeah.
Yes.
So I would have thought that with 12 bounds, that's kind of the lower dimensional system to simulate when you have the stratification. So why is that taking longer?
Sorry, this so yeah, so this is just an error bar estimate of, we're estimating what is the probability of finding a system with 12 bonds instead of 11. I don't really know why, why these error bars are all different.
No, I meant, I guess the last column. So you said that this thing means what's the speed up that you get with stratification versus Brownian dynamics?
Yeah.
And I guess if I understood, I mean, perhaps with these like final slides that you were going to show, I understand, but I like the way I see it is like stratification is faster because you are working in a lower dimensional space. Most of the time, or like you kind of reduce the dynamics to.
It's not that we're working in a lower dimensional space. It's that it's faster because we can add and subtract bonds much more efficiently, and then we can also take steps, fix bonds. We can take much bigger steps when we can fix bonds.
I see. Okay, so that would only help in dynamics then.
This problem, it depends on the parameters that I choose for my simulation.
Okay.
So if, for example, I chose a higher sticky parameter, so here this is from sticky parameter 2, some measure of the strength of interaction. If I chose like 6, I think we would have a much better ratio for up here.
Okay.
So because for the value of the parameter that I chose, most of the stratification samples are in this region. So that's probably why we get a better speed up there, why we see efficiency there.
Okay.
Yeah.
Okay, I think you could continue.
Okay, so I'll just say very briefly how this works.
Just Miranda, we're a little over time, so.
Oh, okay. Sorry, I didn't know how long I had.
10 minutes ago.
Okay.
Oh, 10 minutes ago. Okay.
But just be
Sorry.
wrapping it up now, I think.
Okay, sure. I mean, I don't really have to say anything. Okay. Yeah, so this slide is just to say what I said before, that we propose, so our points are really a collection of, like a point and configuration space combined with a set of labels describing which equations are active. So a step in a sampler chooses new labels according to some probability. And then with that set of labels, it chooses a point on the new manifold according to some density with respect to the Hausdorff measure. And then we do an acceptance rejection step, which looks like this. And this, you can show that this satisfies detailed balance with respect to the right measure that you're trying to satisfy. If we're over time, I'm just going to skip everything then. So yeah, so I'll skip to the end. So I guess I have many questions. So I'd like to learn about new examples where this kind of idea of adding and subtracting constraints can be used. How do we make it more efficient for larger n? How do we add in sort of Hamiltonian or geodesic methods? We're working on trying to make it dynamically accurate. And then an issue that I find very intriguing is when constraints become linearly dependent. So I'm showing some examples here of graphs in 2 dimensions for which the edges are linearly independent, and how do we deal with those in a sampler? Okay, so thanks for your attention.
Okay, thank you. Are there any more questions from Miranda in the room? Matthias, any questions?
No, I'm good.
Okay.
I mean, I would have been interested in the algorithmic details, but yeah.
Yeah, I think it's very interesting. I think I need to study it a bit more. Definitely like to see how we could work with that. Okay, I think we just thank Miranda and everybody for their talks today. And we'll resume the in the flesh session tomorrow morning. Thank you, Miranda.
All right, thank you.
Thanks.
Bye now.